Hello everyone, welcome back to Introduction to Probability in the Statistics course. In this video, we discuss the basics of parameter estimation in the statistical inference. So far, we have covered the basics of probability, including random variables, expectation, and also some well-known distributions, such as normal distribution in the case of continuous distributions, and also Bernoulli and binomial distributions. In this video, we talk about parameter estimation. And also the lecture notes for this video are available, and the link is given in the description below. So what is statistical inference? In a typical problem, we have a random variable, and we call this random variable x, whose probability density function, or PDF, or probability mass function is unknown, right? So PDF is what we use for continuous distributions, and PMF is what we use for discrete distributions. And for the purposes of this lecture, we treat them very similarly, right? Because we assume that either we have two categories. Either we don't know the functional form of these two functions, or we know the functional form, but there are some unknown parameters in them, right? So think about this as a Bernoulli distribution. We know what the probability mass function looks like. If the parameter is p, means that probability of x equals 1 is p, and probability of x equals 0 is 1 minus p. But we may not know what the true p is in this case, right? So that's our goal, to find that parameter. And for the sake of generality, in this case, we call unknown parameter or parameters theta to represent everything that we need to estimate or find. And also the other piece here is that we're going to focus on the second scenario here, where we assume that we know the functional form, but there are some unknown parameters that we want to find in that function that we have. Examples of these, as I mentioned, we can think of this as a Bernoulli distribution or a binomial distribution, where the number of trials, or n, is known. You want to find the probability of success, p. Or you have a normal distribution where you don't know the mean, but you assume that you know the variance. Or in some cases, you may not know mean and variance altogether. To make this a little bit more sense, let's look at another example. In this case, on the right side, we have a histogram plot. Of course, this is more like a density plot because we made sure that the area under this curve is 1, of balance for a credit card data set, right? So this is the balance that people have, on their credit card. And I do believe that there are 400 data points or samples in this data set. So you can see that most people, have lower balances, which is great. And, let's say we want to, approximate this with the probability density function of the exponential distribution, as you can see on the left side. And why exponential? Because the nice thing about exponential distribution is that it's non-zero, the values that you can see on the y-axis, when x is greater than 0, which makes sense, right? Because typically we do not have negative balance if we assume that, balance is always a number greater than or equal to 0. And then the question is, well, what should be this scale parameter theta of the exponential distribution? So you can see that different values have different rates of decay. In this case, obviously all of these, they go to 0 as x increases, but how fast this happens depends on that scale parameter. And we want to solve some kind of like a matching problem, like what value of theta gives us the best approximation for what we have on the right hand side. It's not going to be super accurate because you can see on the right hand side that sometimes these bars that we have, they go down, then they go up slightly, which is not necessarily the same as exponential distribution, but the goal is to make it as close as possible to the exponential distribution. So now let's look at a few terminology that we need to know when we talk about statistical inference. So in general, when we don't know, certain things about the distribution, we need to have a couple of observations or realizations of that distribution. And we assume that these sample observations have the same distribution as x. So that's like the most important thing. And remember, since, like let's say you have exponential distribution as what you saw in the previous slide. So every time I pick a sample realization, that by itself is a random variable, right? Because it's never just a fixed constant, right? It can change every time I draw a number. So in this case, what we have is that we have this x1 to xn, and these are the random variables that they correspond to those observations. And n in this case is called the sample size. And when a sample drawn, the observed values or realizations of these samples are represented using lowercase letters, right? So this means that when I, at first I use uppercase x1 to xn, means that I want to select, let's say n equals 10 observations from this exponential distribution. And obviously, because of this sort of like peak that we have around 0, most of them are going to be close to there, but we don't know exactly where they are. But once we actually draw samples, now we know what they are, right? Because we just, pick some values. And in that case, we show them using lowercase x1 to xn. And then the final thing that you need to know is that in general, in order to solve these problems, we need to find a function of these random variables x1, x2 to xn. And this function is called a statistic, right? So for example, a very simple statistic is what is known as the sample mean, meaning that, in this case, we have n random variables, x1 to xn. We're going to add them together and then divide them by the total number of samples. So in this case, this means that, we have a general recipe or general formula that depending on what these n values after we draw them they are, we can plug them into this statistic and get the corresponding estimate of the sample mean. So we can visualize this too, actually. So also something to keep in mind is that in terms of terminology, there's one more thing we have to pay attention to. In this case, that we have one random variable, and we assume we have n observations or realizations of these, where each of these we treat them as random variables. We call these x1, x2 to xn as being independent and identically distributed, which we show that shorthand using IID. So that means independent and identically distributed. And in other words, we have a random sample of size n from a common probability distribution. And so on the top left corner here, you can see that we have a population. This is the set of all subjects we are interested in this case, for example, a binomial distribution with parameters n and p. And let's say, the unknown parameter here is this probability of success p, right? And n is unknown. Again, we do this something 20 times. And, each time we get either success or failure, each time that we do this random experiment, we get a different number of successes, and we want to know what the true p is, right? So in this case, our parameter that we want to estimate is p. In order to solve this problem, we need a sample, and that's this x1 to xn that you see on the top right corner. And then we calculate a function from this sample, which we call it a statistic, and that's this function t. And now this statistic, its goal is to estimate the unknown parameter p, right? So for every statistical inference problem, you really need to have this picture in mind, that what the population is, what is the sample and parameter and a statistic. And in this case, we are mainly interested in finding suitable or appropriate statistic functions for solving different inference problems for different distributions. So that's just what we just discussed. And remember that there's a difference between estimator and estimate. An estimator is the function of those random variables, IID random variables, x1 to xn. But once we actually, make observations and we know the realizations, and we plug it into the same function, and you can see here we are using lowercase x1 to xn, we call this an estimate, right? And the most common form of estimator is what we call as a point estimator, which means that we get a single value as an estimate of the population parameter. And in this case, one thing that you really need to know is this method of maximum likelihood estimation, or MLE. It is so famous and popular that people usually just call this MLE, which stands for maximum likelihood estimation. But in many cases, point estimates may not be enough, and we may want to also know something about the variability associated with the estimate. And there are techniques that we cover in future videos, like estimating intervals, and then confidence intervals, sampling distribution, and so on. So solving MLE problems can be kind of, complex from the mathematical perspective, because we have to do a lot of multiplications, then taking the logarithm of the result. But right now I want to explain to you what maximum likelihood estimation is. So here's the scenario. Assume that the random variable x, which is our population, is a normal distribution with unknown mean mu and a known variance, right? So we want to find the mean of that normal distribution. So the idea is this: if I make one observation, and that observation is 2, right? So I can put a normal distribution, which is centered at 2, that's like that peak that you see on the left side for the blue curve, and that would be our likelihood function. So if I tell you what's the most likely value, then you just have this blue curve, and you'll be like, oh, the most likely value for the mean is actually 2. Well, that's kind of like obvious. But what's happening here is that now let's say I make 2 observations. So I know that one time I got 2, the other time I got 4. If we don't know anything about a statistical inference, and I ask you that I want to know the mean of a normal random variable, and I have 2 observations, 2 and 4, you'll probably say, well, let's take the average of them, right? 2 plus 4 is 6, divided by 2 gives me 3. So, but how do we get there? So from a statistical perspective, what we really do is that we have this normal distribution, which is centered at 2, that's the blue one. And then we have this orange one, which is another normal distribution centered at 4. And if we multiply these 2 bell-shaped curves, you get a new one, which is this green one, right? And in this case, you can see that if we look at what point this green curve or green function achieves its maximum is at x or mu equals 3. This is what we get on the x-axis. And that's what we usually call it as argmax here, right? Because argmax means that we don't care about the maximum value. We want to know where the maximum occurs. And the maximum of the green function, which is multiplication of the blue and orange ones, occur at mu equals 3. And that's actually, your MLE, or maximum likelihood estimate. So now we want to formalize this and, mathematically introduce this concept of forming the likelihood function. So let's say that you have a Bernoulli distribution. Bernoulli distribution has a probability P, and that's the probability that we get heads or we get x equals 1. And we want to construct the likelihood function. So in this case, you make n IID random variables, x1 to xn, and you find the probability mass function, or PMF, for each observation. And we talked this in the previous video. We can write this in one line using p to the power of xi, 1 minus p to the power of 1 minus xi. So if xi equals 0, then you get 1 minus p. And if xi equals 1, then you get p to the power of 1, which is p. And so now, if you look at the joint probability of these observations, because these things are independent, that's the product of individual probabilities, which gives you this product. That's what notation that we use here. Product from 1 to n of pxi, 1 minus p, 1 minus xi. And now we use the fact, so this is what is known as now your likelihood function, right? And the thing that is very important is that the likelihood function is a function of the unknown. That's why here very explicitly we use uppercase L for likelihood function. And then in parentheses we have P, because this is a function of the unknown, which is P, which is product of Pxi 1 minus P 1 minus Xi. And now you can simplify this, because if I multiply Pxi for different values of Xi, then we have a summation in the exponent, right? So this is P to the power of sum of Xi's, and the same thing happens with the second term that we have here. Now we see we can separate them because it's product of the terms. So in this case, your likelihood function is this unknown parameter P raised to the power of all Xi's. And remember, when you use lowercase xi, these are actual values that you get. So you do something n times, and each time you get either 0 or 1, so it means that each xi is either 0 or 1. And this sum of xi's represent the total number of successes in the sample, right? Because remember, for every failure we get 0, which does not change the summation. So in other words, if you want to wrap up everything here, the likelihood function, which is this uppercase L as a function of P, indicates how likely different values of P are to produce the observed data that we have, right? Because in reality, if we have, let's say, 20, n equals 20, we do something 20 times, each time we get 0 and 1, then we can just count the number of successes we have. And that's the idea of argmax that I just mentioned to you, meaning that we don't care necessarily about the maximum value of LP, we care about at what point the maximum occurs. And in this case, you can see that, of course, if the sum of xi's is all equals 0, then this is maximized for p equals 0, and we show the estimate by p hat. And this makes sense because if we get all zeros, means that the probability of success should be 0, because we never get one. And if in all cases that you do, you get 1, which means that the summation of xi's equals n, then p to the power of n is maximized by taking p hat equals 1, right? Because all the evidence is that then we get 1 every single time, so the probability of success must equal 1. But the interesting thing is when the sum is not 0 or is not n, right? So not these two extreme cases. And in this case, now you have to use calculus, right, to find the derivative of this function, the likelihood function, and set it equal to 0 to find a critical point. And in this case, if we assume that the total number of observed successes is k, right? So we have p to the power of k, 1 minus p to the power of n minus k, and you take the derivative of this with respect to p. So this gives us the derivative of the first term times the second term, and then plus derivative of the second term times the first term. And then, you can simplify this. You can see the full math here, but you can simplify this and set the derivative equal to 0. And if you just multiply this k by 1 minus p and then n minus k by p and solve this problem, you can see that our estimate here is k over n, and k is the number of successes. So here's the critical thing. So right now, this is our estimate if we know what these x1 to xn's are. But in reality, we don't know, and we want to do this problem in a way that we can give you a general recipe or formula. So that's why now we replace this lowercase x's with uppercase x's, because these are actually random variables. And you also find your statistic, which is this function t, which is known as the sample mean, meaning that if you have a bunch of observations, simply find the average, right? 1 over n, summation of xi's from 1 to n. And so in order to kind of summarize this, we say that the maximum likelihood estimator for the success probability p in the Bernoulli distribution is the sample mean. And in this case, also, we can look at this a little bit more like visually. So you can see that if we have this likelihood function, which is on the left side, right? So this is how it looks like, that formula that we found. If n equals 20 and k equals 10, right? So you get this peak, right, at p equals 0.5. right? So that's your argmax. And that's exactly what we just talked about, right? So you find the likelihood function. You can, in this case, plot it since it's a univariable function and see where the maximum happens. But a very nice trick that we can use is that once you find the likelihood function, you can take the logarithm of that function. And since logarithm is a monotonically increasing function, the parameter that maximizes the likelihood function does not change, right? So you can see here on the right hand side, I take the logarithm of what we have on the left side. So this is the logarithm of the likelihood function, which we call it log likelihood function. And you can still see that the maximum happens at p equals 0.5. Although the value on the y-axis is different, as we know, because we're taking the log of whatever it's on the other side. But the fact that matters is that the maximum or the maximizer or argmax has been preserved. And this is very helpful, right? So why is this helpful? You can see this in the next slide. If I have this product of probabilities, right, I know that the log of products is the sum of the logs, right? So in this case, what's happening is that I get this log of pk, and because k is an exponent, if I take the log based on what we know from calculus, we get k times log of p, and then plus n minus k, which is again the exponent, log of 1 minus p. And now, like before, you take the derivative with respect to p, set this equal to 0, and that gives you the same sample mean. So in the next slide, we can just summarize the entire thing that you have to do to see how easy it is, even though the math can get a little bit complex. So you form the likelihood function, which is the products of the PDFs or PMFs. We just use F here to represent all of them. So that's the uppercase L, your likelihood function. And in general, we use theta to represent unknowns. And then we take the natural logarithm of these. So that's what gives you this curly L, which is log of L theta. And using the nice property about the logarithm, you can see that this is the sum of the logs. And then you set the derivative of this log likelihood function with respect to theta equal to 0. So we know the general recipe or formula here. So now we can extend this to as many distributions as you want. So one example of this is the exponential distribution. I don't go too much into details because you can see you need to really write this down yourself to see all the steps. But you start with PDF or PMF. This is continuous. We start with the probability density function, which is 1 over theta exponential of negative x over theta. And this is only defined when x is greater than or equal to 0. Also, theta here should be a positive scalar. So you form the likelihood function, which is the product of PDFs. You can, because 1 over theta is multiplied by itself n times, you get 1 over theta n, and then exponential of the sum, right? These things happen in the exponent. You take the log of this, which gives us negative n log of theta, and then that log and exponential are inverse functions, so it disappears, which is extremely helpful. Another benefit of using the logarithm function. And in this case, you get this very nice simple function, negative n log of theta minus 1 over theta sum of xi's. And the next step is to find the maximizer, which is something you do by taking the derivative with respect to theta. And using what you know from calculus 1, you can take this derivative, set equal to 0. And again, we see that the estimate here is sample mean. And as I said, sample mean is something that happens all the time, it looks like it, right? That it's extremely helpful for example, finding the parameter P of Bernoulli, for the scale parameter of the exponential distribution, and also other things. So what are those? Like also normal distribution, right? But in this case, to make this problem a little bit more interesting, so we assume that we have a normal distribution, which you have the PDF here, with mean theta 1 and variance theta 2. So in this case, you can see that again, we can find the likelihood function, but since we are assuming that both mean and variance here are unknown, the likelihood function is actually a function of both theta 1 and theta 2, right? So as I said before, when we say L of theta, we mean like all the unknowns. Doesn't need to necessarily be only one. It can be more than one. But the rest is very much the same, right? So you find the product of these PDFs. Again, you have this first term that gets multiplied n times because there's no xi in it. And then the other exponent here where we have exponential becomes sum of these xi minus theta 1 squared and whatever we have in the denominator. But the nice thing is that since we can take the log of this likelihood function, things become really simple using the fact that, again, log and exponentials are inverse functions. And now what we need to do is to set the derivative of this equal to 0. But since we have two kind of like variables, theta 1 and theta 2, first you take the derivative with respect to theta 1. And this is technically a partial derivative. So partial derivative is a fancy name for derivatives when you have more than one variable. And the way that works is when you take the partial derivative with respect to theta 1, you assume that theta 2 is constant, right? Assume that it's just a fixed number. So the nice thing is that when you take derivatives, you treat theta 2 as just the way you do constants. And in this case, you can see that that's the partial derivative with respect to theta 1. And if you set this equal to 0 in this case, you can see that then whatever we have in the numerator should be 0, which means that sum of xi's, I from 1 to n, and then you have that negative theta 1, that term should equal to 0, which means that theta 1 should be 1 over n sum from 1 to n of xi's, and that's again sample mean that we saw previously again and again. But the nice thing here is that in terms of like a practice problem is that now you also have that second variable theta 2, which is the unknown variance. So now you have to take the partial derivative of this log likelihood function with respect to theta 2. And if you look at this and do the stoic math, you can see that this is actually what we call it as like the sample variance, right? Because what it's basically telling us to do, if you look at this formula, is by subtracting each xi by the mean that we estimated. So we don't know exactly what it is, but we have estimated that using that theta 1, which was the sample mean. And then we find the average squared differences. So all in all, this tells us that if we want to find maximum likelihood estimators for the mean and variance, for the mean is the sample mean x bar, and then for the variance is this 1 over n sum from 1 to n of xi minus x bar squared. There is one last thing that we need to cover here, and that's the idea of unbiased estimators. So what this means is that when we have a population, when we have different samples or realizations of the same size, if we can repeat this process many times, ideally we want to make sure that we get the true unknown parameter, right? And that's the idea with unbiased estimators. An unbiased estimator has an expected value equal to the true population parameter that we want to estimate. So this means that if you have an estimator theta hat, which is that function t with random variables x1 to xn, which are the uppercase ones. So this is now another random variable, so we can take the expected value of these, and we want to make sure that expected value equals the unknown parameter that we are trying to estimate. And this is important because it means that on average, our estimate will be accurate, right? But if you have biased estimators, this means that you will have a systematic overestimation or underestimation of parameters. So in this case, once we found theta hat 1 and theta hat 2 for normal distribution, the first one was for the mean, the second one for the variance, now we can look at their expected values. So expected value of theta hat 1 is expected value of this function here, that's the sample mean, and using the linearity of expectation, this means that we can find this expected value of each xi, add them together, divide by n, and in this case it's super easy to see that this is actually the quantity that we want to estimate. And then for the variance is a little bit more sort of like complicated, right? Because we cannot directly solve that problem, but we can use this very simple trick where we add and subtract theta 1 And in this case, you can see that if you take the expected value of this theta hat 2, we have two terms. And in the next slide, we can see that now the first term, the expected value is theta 2, whatever we want to find. But there is this small correction that the second term gives us theta 2 over n. And this means that if we do the math, right, and factor theta 2, we get this n minus 1 over n times theta 2. And this means that theta hat 2 is a biased estimator, right? So if you look at it, we don't exactly get theta 2. Although this doesn't really matter, because if n it goes to infinity, right, so the limit of n minus 1 over n as n goes to infinity is 1. But if you really want to correct this, especially for small sample sizes, like n equals 5, 10, things like that, then you can multiply your theta hat 2 by n over n minus 1 to cancel that n minus 1 over n. And this gives us this formula, which is 1 over n minus 1 sum of squared differences. And this is why you can see that there's always this question when you find the variance or estimate the variance of bunch of numbers, that either you have to divide this by n or n minus 1. The difference is that, well, if you divide it by n minus 1, technically you're using the best approach because this is unbiased, right? So this is why it's known as this s squared. So this is unbiased right now because its expected value equals theta 2. But if you divide this by n, which is more intuitive, then you have this small factor that you see in the equation on the top. So this is a very brief summary of why maximum likelihood estimation is important in a statistical inference, intuitively what it does, and mathematically you can see the different steps to form the likelihood function, the log of likelihood function, and then finding the maximizers. I hope you found this video helpful.